Bismillahirrahmanirrahim. My dear students, Assalamu alaikum. I hope all of you are fine. I'm Irene Parvin. Welcome to all to our online chemistry first paper class, English version, arranged by KPB School and College. Today I will discuss two important topics under chapter 3. First one is relation between hybrid orbitals and shape of covalent compounds. Another one is effect of lone pair electron on molecular shape. You have already known about hybridization, but for your convenience, I'm repeating it again. The process of mixing different orbitals of different energies to form same number of orbitals with equivalent energy in valence shell of an atom during reaction is called orbital hybridization. The new atomic orbitals formed are called hybrid orbitals. For example, in beryllium, the valence shell of beryllium is second shell, and here two different orbitals s and px mix together and produce fully new 2sp orbitals. You have known from definition that different orbitals of different energies mix together to form same number of orbitals. Look here, here s and px orbital mix together. Here two orbital mix and form two hybridized sp orbital. If you look at atom boron, you see here that the valence shell of boron is second shell, and here one s and 2p orbital mix together and form three hybrid orbitals, that is sp3 sp2 orbitals whose energy are same. And if you look at carbon atom, you see here one s orbital mixed with three p orbital, px, py, and pz orbital, and after mixing, they produce total four hybrid orbital, that is 4sp3 hybrid orbitals, and their energy are same. Only because of hybridization, carbon form so many compounds in nature, almost more than 80 lakhs, and other atoms which form hybridization are beryllium, boron, nitrogen, oxygen, etc. On the basis of hybridization, the regular shape of covalent molecules can be explained. For this, now I will discuss VSEPR theory. Valence shell electron pair repulsion theory, that is VSEPR theory. VSEPR theory was developed by Gillespie and Nyholm to predict the geometry and shape of covalent molecules. According to Vesper theory, the electron pairs around the central atoms in a molecule should be arranged as far apart as possible. I repeat this again. According to Vesper theory, the electron pairs around the central atoms in a molecule should be arranged as far apart as possible. What is the reason? Because this decreases the repulsion between two electrons and gives stability to the molecule. You know, molecules or atoms always try to attain their stability. And the shape or geometry of a covalent molecule depends upon the number of electron pairs. Shape or geometry depends upon the number of electron pairs present in the outermost shell, and both the bonding pair and lone pair of electrons in a molecule around a central atom determine the shape of the molecule. I repeat it again. The shape or geometry of a covalent molecule depends upon the number of electron pairs around the central atoms in its outermost shell, and both the bonding pair and lone pair of electrons in a molecule around the central atom determine the shape of the molecule. And pairs of electrons in the valence shell repel one another since their electron clouds are negatively charged. Actually, uh, the hybrid orbitals of a central atom in a covalent compound with special orientation determines the shape of compound. So, the molecular shape and bond angles of different covalent compounds are controlled by the nature of hybridization of the central atom. I repeat it again. The molecular shape and bond angles of different covalent compounds are controlled by the nature of hybridization of the central atoms of the compounds. For example, look at the figure, please. Look at the figure, please. sp hybridization forming two hybrid orbitals and produces linear structure. Look here, barium chloride, here sp hybridization occur and forming two orbitals, two sp orbitals, and this is the linear shape of the molecule, and its bond angle is 180 degree. And next, bronze trichloride, here sp2 hybridization forming three hybrid orbitals, and produces trigonal planar structure. This structure is trigonal planar structure, and their bond angle becomes 120. Now, sp3 hybridization forming four hybrid orbital produces tetrahedral structure. Look here in methane. Here sp3 hybridization occur, and for these four hybrid orbitals are created, and that's why the structure of methane is tetrahedral. Look here, the tetrahedral structure of methane, and the angle between hydrogen carbon hydrogen is 109.5 degree. Now uh, I will uh, discuss regular shape of some compounds such as beryllium chloride, boron trifluoride, and methane molecules in details. You show in this slide the regular shape of beryllium chloride is linear shape. In beryllium chloride, valence shell of central atom, that is beryllium, central atom is beryllium, contains two hybrid orbitals. Two hybrid orbitals, then molecular shape become linear. Since it contains two hybrid orbitals, so its molecular shape is linear. And you see here definitely sp hybridization occur, and then bond angle become 180 degree. Bond angle become 180 degree. And now in boron trichloride, the boron trichloride or boron trifluoride, the valence shell of central atom, that is boron, contains three hybrid orbitals. Central atom is boron here, and it contains three hybrid orbitals. Then molecular shape becomes triangular, triangular planar. Here sp2 hybridization occurs at central atom, then bond angle becomes 120. Bond angle becomes 120. And another example is methane. In methane, valence shell of central atom, that is carbon, valence shell of central atom, that is carbon, contains four hybrid orbitals. Carbon contains four hybrid orbitals, then molecular shape becomes tetrahedral. Here sp3 hybridization occurs at central atom, that is carbon atom, then bond angle become 109.5 degree. Here this is the tetrahedral structure of methane. So, from the above discussion, it is clear that the shape or geometry or structure is fully dependent on hybrid orbitals, nature of hybrid orbitals. Now, I would like to discuss Effect of lone pair electron on molecular shape. Sometimes of regular shape of molecule. Sometimes regular shape of molecule is distorted or distortion of regular shape of molecule is occurred sometimes. To understand distortion of normal shape of molecules, you have to know about bond pair and lone pair electrons. Though you know about these two definition, but I will repeat it again for your convenience. The electron pairs in the valence shell, definitely valence shell, which are formed bond are called bond pair electrons. I repeat it again, the electron pairs in the valence shell which are engaged in bond formation are called bond pair electrons. On the other hand, the electron pairs left in the valence shell without forming the bond are known as lone pair of electrons. Now, distortion of normal shapes of molecule can occur due to repulsion of different number of lone pair electrons on different bond pair electrons. For example, I will explain why distortion occurs in ammonia and water molecule. Look at the figure, please. Here you see the structure of ammonia molecule. Though the shape or structure of ammonia molecule was supposed to be tetrahedral and bond angle 109.9 degree like this, each structure and bond angle is triangular, triangular, pyramidal and 107 degree respectively. But what is the reason? The reason is that the central atom contains only one lone pair electron. Ammonia contains only one lone pair electron. Look at the figure, please. Here, ammonia molecules. The center atom is nitrogen and it contains only one lone pair electron. Lone pair electrons in sp3 hybridization. Then normal tetrahedral structure of the molecule is distorted when I repeat it again, when the central atom contains one lone pair electrons in sp3 hybridization, then normal tetrahedral structure of the molecule is distorted and becomes triangular pyramidal shape. That's why ammonia gain a triangular pyramidal shape because ammonia has one lone pair electron. Now, another example is water. The shape and bond angle of water molecule is V-shaped and 104.5 degree respectively because the central atom of water is oxygen which contains two lone pair electrons. Central atom of Oxygen contains two lone pair electrons in sp3 hybridization. Then, normal tetrahedral structure of the molecule, that is water molecule, is more distorted and become V-shaped, and bond angle becomes 104.5 degree except 109.5 degree, and that's why water molecule gain V-shaped structure except tetrahedral structure. And one thing is very important: when central atom of a molecule uh, contain contains all the bond pair electron in their valence shell, then the shape of the molecule is normal. And when the central atom of a molecule contains one or two lone pair electrons, then their structure or geometry is distorted, and they gain extra or exceptional shape rather than usual shape. I think all of you understand these two topics very clearly. No more today. Thank you, everybody. Take care. Bye.